Thank you.
Do they care about the audio?
All right. So today I'm going to show you guys how to do event selection in Jana. And specifically, we're going to be looking at omega photo production, where in the end, tomorrow, we'll be looking at spin density matrix elements, but I'm going to show you guys how to get started. And if you aren't familiar, Jana is our main framework for doing reconstruction. We went into a lot of detail about how Jana works during the workshop in 2013, and those sessions are recorded. So in the interest of time, we're not going to repeat that information, but we're going to try to go very briefly through some of the basics and get us into root, where we will continue doing the analysis tomorrow. All right, so for this workshop, we're working with simulated data in a nice controlled environment. So the data that we're using is this launch. We had a launch where we simulated a whole bunch of data called Sim1, and we designed it to be similar to what we thought the spring run that we just took might look like. And if you want some details on it, the information's at that link. But in general, this data was the beam energy was between 4 and 12 GeV with a coherent peak at 9 GeV. And we simulated an EM background similar to what we might expect for the early GlueX physics data. The data themselves for the simulated data are located on tape at that spot, and also for now on the volatile disk. But we got a file here on the virtual machine that you guys can play with. And what we're going to be working with is the reconstructed data. So we've generated all this Pythia data that we're going to be looking at, and we did the reconstruction, and the output of the reconstruction is in these REST files, .htdm. In other words, nothing low level is left. We have reconstructed showers and tracks to work with, and we made this data by running the Dana REST plugin. So in general, it's way faster to just do reconstruction first and then do your analysis. That way you don't have to repeat track reconstruction every time you run over the data. So if you're looking at an EVIO file, just first run Dana REST, make a REST file, do the reconstruction, and then run your stuff. All right, so let's inspect the data that we have. General rule of thumb is to always run the monitoring HIS plugin. So what this does is it just histograms everything relevant about the reconstructed data that we want to see, such as track and shower distributions, particle ID, etc. And the REST file, the reconstructed file that we have to work with, is located in that spot. So I'm going to do that now. I'm going to get that started. Since this is being recorded, you don't have to, type to keep up. You can look at it later, but I want you guys to see how you do this.
So this is creating the REST file.
No, the REST file is already created. It's on the virtual machine at this spot. Right now, all I'm going to do is run the monitoring histograms, and we're just going to look at some basic information about the data. So I'm going to go into the Scratch folder where we have some space, and then there are some links there. So this is the data is located in another other spot, but I went ahead and put a soft link right there, so it's convenient.
Bigger font.
You need a bigger font?
Yeah.
All right.
Control plus.
All right, how's that?
Can you also do alias ls dash color equals never?
Alias ls what?
To single quote ls
Single quote.
Yeah.
ls space dash color equals never.
Yeah.
Most of quotes.
There.
No, it's with Matt. Is it?
Can you say Matt, please?
Never mind.
Keep your.
Okay, we're gonna roll with it, okay? All right, so HD root is the main program which we do, when we're running with Jana. Then we're gonna paste the file, and then I'm gonna tell it to run with the monitoring HIS plugin, and it'll take a while to run over everything. So instead, I'm just gonna look at the first 5,000 events in the file. So So this is going to start running, loading geometry and calibration constants. All right, so it's running. We'll get back to that in a second. But I mean, the main reason you want to do this is you should always just run this in order to make sure you can check to see if the data makes sense. Did the track reconstruction work? Don't take that for granted. You can look at these histograms and it will tell you, are the data calibrated? And you can use this to diagnose any source of, analysis problems you might have. All right, so it finished. If I do another ls, I now have this root file. So let's open it up. All right. And if you are having trouble seeing this, if you're sitting in the back, this is shared on the Blue Jeans. So if you're sitting way in the back, it might be easier for you to just look at it in Blue Jeans if it's too far to see. All right, so I open this file. I have this independent folder, and then I've got all these different things that are histogram. So first, let's just look at the number of reconstructed objects. So I'm going to set this to log scale because the RF time is dominating it. All right, so we see star counter hits. There's an average of 6. Time of flight hits. We have an average of 20. A lot of them because of EM background. We have a fair number of B-cal showers, F-cal showers, time-based tracks, etc., etc. Now, D-beam photon is missing. Now, does that mean that there was a problem? No, that means it was off the scale. So if I go down to number of beam photons, oh, this is old software. All right, so this is out at 100. So there are photons in the data stream, but they're from 60 to 100 photons in this data stream. This is something we'll have to deal with. It'll be difficult for us to select photons in the data. So I'll show you how to do that. All right, so in reconstruction, I can look at tracking. So positively charged tracks. Let's turn off log Z again. So this is just the momentum and theta for all of the positively charged time-based tracks. Same with negative. So you can see in general things are working. And so there's other things you can look at as well. F-cal shower, reconstructed position, F-cal shower energy, B-cal shower energy, F-cal shower position, etc. B-cal. So you can use these to look at the data and just see if it works. But basically, if there's something you want to look at, it's probably already histogrammed. You could just run this, and it'll have it. All right. So now, let's talk about reactions and particle combinations and channels. Now, so what I'm going to do is we're going to generate a plug-in for Jana that we're going to run to do our analysis. And I'm going to do this live from scratch. So this is a little dangerous. But for reference, the final plug-in is on the virtual machine. So you can look at it for reference. Don't feel like you have to code to keep up. And I'm going to show you how to reason through how to write the code to do the analysis that you want to do. So the way you do this is you create the plugins by running some Perl script. So let's close root. And I'm in the Scratch folder. Well, let's go to HallDMI. So HallDMI is generally your personal area where you can make plugins and do whatever you want. Okay, so then I'm going to run this Perl script make reaction plugin, and I'm going to give it a name. So I'm just going to call it session 2 because that's where we are in the workshop, and it made a bunch of files. So let's open one of these. All right, let's go into. So if I do an ls, there's a folder session 2, and if I go in there, there's a bunch of files. All right, and so we've got some code that was generated. So we're going to work with this template code to write the analysis that we want to study. And in general, you can follow the example code, uncomment it, tweak it, etc. So it's set up to already be close to what you might want for a channel, and then you tweak it to what you want. All right, so now there's this object called D-reaction, and it's a collection of D-reaction steps. So the idea is here at the bottom right, you can see, the channel we want to analyze, gamma p to omega p. The omega goes through a 3 pi decay, and the pi 0 goes to gamma gamma. So what we're going to do in the code is we're just going to set up the reaction to follow that decay channel. So it has 3 steps. So we're just going to set it up like so. So if I look here, so reaction definition here. So this is required. So we already have a commented out example that's actually kind of similar to what we want. So it already has 3 pi and the pi 0 to gamma gamma, but it doesn't have the rho. So I'm just going to set that up now. So
Recording is
Someone needs to mute a mic.
all right, so I've set up the first one.
Yeah, you have to you have to mute your sound and turn on your mic.
okay.
All right. So what I've done is, so you can look at the first one, set initial particle IDs gamma. And these are enums that are defined in this header file up here. But you can pretty much guess what the names are. So a target is a proton target. Final state, it'll go to an omega proton. And so then, in the next step, the omega is decaying to 3 pi. So we have initial omega, 3 pions, pi plus, pi minus, pi 0. And then we have the pi 0 going to gamma gamma. And so what we're doing at each step, we create the step, we set the information, and then we add it to the reaction. So we're just filling out these steps at the bottom right in the code. All right. All right, so now we've told Jana basically what channel we want to look at. So what do we want to do with it? Now we want to make particle combinations. So let's open.
What section of code did you do that in?
That was the D-reaction factory. And so now I'm going to open the event processor. So here, so that was a factory. What it does is it will make the D-reaction objects whenever they're requested. But it won't do anything until we actually request them. So what we're going to do is request the analysis results. So what I've done is I've gone into the event processor, which is what Jana runs, and in this event function, it's executed every event. And in this required section, I've just said, okay, I want the analysis results. Jana, give them to me. All right? So we're going to save it. All right, so now I'm going to compile this and run it. So scons install. Open a new terminal.
Where do we find the code examples? Are they on the machine already?
So the final answer is here. This is what I'm going to end up making. But right now, I made it from scratch. What I made from scratch, I ran this Perl script, and it generated all that code. And now I'm just editing what it already made. All right, so this is being recorded. So If you miss something, you can always go back and take a look. All right, so now I made my plugin. I'm going to run over that file with my plugin and the monitoring hiss. And I'm just going to do the first 1,000 events. All right, so now what's it going to do? It's going to take all of the reconstructed tracks and reconstructed showers and try to match them to the reaction that I wanted. So what it's going to do is it's going to try to form different combinations of particles that match that reaction. And then we can take a look. So in general, with particle combinations, so what we want to isolate our channel. This is our channel. So GlueX is going to detect the beam, photon, and final state particles. You know, proton, 2 pions, and 2 gammas. And so what we're doing here is we're going to build all combinations of detected particles that match our channel. So right now I haven't put any particle ID cuts on. So instead, all particles with the desired charge are going to be candidates. In other words, every positively charged particle that we detect could be a proton or it could be a pi plus until we put some kind of particle ID cut. So for example, we're doing this channel. In order to do it, we need to reconstruct at least 2 positively charged tracks, 1 negative, and 2 neutral. And let's say we reconstruct a little bit more than that. Let's say there's a ghost track or something. We've got an extra negatively charged particle, or maybe it's a different channel entirely. And then we have 4 neutrals instead. So the way this works is we build all possible combinations of this. So we test each positively charged particle as a proton or the pi plus. Each negatively charged particle is the pi minus. Each neutral as the gamma. And then, so excluding the beam, there's 24 different possible combinations that the tracks and showers in this event could match our reaction. So that's a lot. So then we need cuts such as particle ID to wean it down, right? So you just start with the complete basis of every possible combination, and then you make cuts to whittle it down such that you try to match what was in the data to your channel. So you saw there was an extra pi minus here. We could cut events with extra tracks and showers, and we can, but we might lose signal because, for example, there's extra things in the event that look like photons but aren't really photons because the shower clustering isn't quite perfect, especially for hadronic showers. It's still improving. But you can have ghost tracks or accidentals, where an accidental track is one that originated from a different beam photon in the event. So, okay, so this thing ran. So let's take an initial look at what we have here. So session 2, that was when I named the plugin. So inside here we have some histograms. Just look at just num particle combos. All right, and so the x-axis is log scale. So I'm going to set log x. All right, so you can see here that we have a lot of combinations. It's never only one combination. Sometimes it's 2, 3, 4, 10. Sometimes there's 100, even 1,000 combinations. Now, this is okay. We haven't done any cuts to narrow it down yet. We just asked for all the combinations. So now we need to select, which one was the proton, which was the pi plus. Was that really, a photon, or was that just a spurious shower from a hadronic? What do we have the right beam photon? We need to make some cuts. But this is just the general basis. All right, so let's start making some cuts. All right, so let's go back to the code. All right, let's go to the D reaction factory. So this is where I defined what the channel was. So if we go down a little further, we can start defining some more things. Let's go a little further than that. So now we can start placing cuts. So for example, you could set a very loose invariant mass cut on the pi 0 as an example. And so we have several things, we have several handles. So before we do particle ID, we know we need a pi 0, we know we need an omega, and we know since we're detecting everything, the missing mass squared should be 0. So let's start with some loose cuts along those lines. So I'm going to cut pi 0 fairly wide around the peak. I'm going to cut the omega also fairly wide. And then I'm going to add an action that tells it I want to cut missing mass squared between near 0 but not quite at 0. All right, so that'll help us. So we haven't done particle ID yet, but that'll help us narrow it down a bit.
What's the false in that argument?
So you could say I want to cut the missing mass squared using the measured 4 vectors or using the kinematic fit 4 vectors. So in this case, we just want to use the measured 4 vectors. All right. Okay, so in general, we isolate our event. We need to cut our backgrounds. These backgrounds could be due to having the wrong particle ID. And in order to do that, you can cut on the timing or energy loss in one of various detectors. You might have the wrong beam photon, so you can cut on the timing to isolate that. You might have an event where you didn't have the pi 0 or the omega, so you can reject those backgrounds by cutting on the mass peaks, et cetera, et cetera. Those are the main cuts. And then how tight you want to cut varies from analysis to analysis. We're going to start with loose cuts because we can always cut tighter later. And then there'll still be some background left even after we do all of this under the omega peak. So you have to either subtract it with sideband subtraction or include that fact in your fits. And there's one thing I should mention. I said it was using every possible particle that was in there to try to match our data, but that's not quite true. We try to reject very likely things that are junk tracks and showers. And so by default, we reject tracks that don't match a hit in either of these detectors. So if your track doesn't have a matching hit in the time of flight, the barrel calorimeter, the forward calorimeter, or the start counter, it's probably junk. So just get rid of it. And require that the showers have some minimum energy of 100 MeV, and that the barrel calorimeter, the showers, are in at least more than one cell.
There's no default cut to reject track max showers?
That happens automatically.
Right.
So
showers already have the ones that are matching tracks approved, and then
right. So this D-neutral shower is showers from the VCal and the FCal that weren't matched to tracks. So there's factory tags pre-select for these objects that do these cuts, and they're automatically applied when we're building the combos. So you could disable these, you could do your own custom cuts, but how it works is beyond the scope of the workshop. There's instructions here. But just know that this is happening automatically just to throw away things that are spurious.
So that's applied to every shower?
Yes.
You can invent your own cuts, though.
Yes.
You don't have to do a cut directly through the interface.
Right. You could write your own factory to do a cut. All right. So in order to get the data to fit on the virtual machine comfortably, I made a skim. So I cut data that was obviously background. And so those cuts I just coded, the pi 0, the omega, and the missing mass squared, those cuts are already on the data in order to fit the events on the thing. And to be honest, for our analysis, this is all we really did in JANA. We took the results from that, saved it to root trees, and then we'll look at the root trees tomorrow. So we wanted to demonstrate things like particle ID, both in JANA and in root. So we'll do more cuts here. We'll do particle ID cuts, etc., and we'll show you mass peaks. But to get to root, the only other cut we did, besides the ones I just showed you, is we require the kinematic fit to converge. And I'll talk about that in a second.
So that run with 1,000 combinations in some events very few, but some,
Right.
that did have these quality cuts already.
On those, yes, it did. But the number of beam photons was off the scale. Sometimes the number of neutral showers, there's a lot of those. But okay, so I placed these cuts. But now let's look at some histograms. Let's see what these mass peaks actually look like. So there we get to the analysis actions section of the code. So the idea here is that these actions, these lines, add analysis action, you're telling the code what you want it to do in the analysis. So there are things that are commented out we'll get to in a second. So but first of all, we want it to histogram some particle ID information. And then we want to histogram some masses. So this is some example code. So we're just telling it, after you histogram the particle ID, I want you to histogram the invariant mass. So we'll histogram the pi0 invariant mass using measured data, and we'll just do 85 bins we're defining the histogram bounds here from 50 MeV to 220 MeV. And then for the missing mass, we don't want to do missing mass, we want to do missing mass squared because it should be near 0.
Spelling.
Thank you. All right. Let's just do 200 bins, I guess. -0.08 to 0.08. And then let's do the omega.
The last which you have
The string?
Yeah.
All right. So the idea with the string is it's going to create these histograms and put them in the file. And we want to make sure they show up in a unique folder. So histogram action invariant mass, I'm calling it twice. Once for the pi0 and once for the omega. So to make sure that they don't overwrite each other, you just have it, so that way it'll show up in a separate folder in the histograms. And so that the threads know which ones to use and which not to use. All right, so let's histogram the omega, 150 bins from 0.5 to 1.1. So I'm just going to histogram where I cut it. All right. So let's go back to my plugin folder where I have all these files. I'm going to compile again. See if this works. Good. All right, then we're going to run. And we'll just do first 10,000 events this time. All right. So I can tell you in advance this is going to look kind of ratty. But the reason is we haven't done any particle ID cuts yet, right? We're just going to look at what every combination of two showers that aren't matched to attract look like, with respect to are they a pi0. But we still don't even have a timing cut on those showers, And with the omega, it's same thing. Every possible combination, it'll be protons being tested as pi pluses, and other various things that were in the Pythia data. So it won't look pretty, but we can see what it looks like to get started.
So past the kinematic fit, right?
No.
Oh.
That was used to make the T-tree for the later sessions tomorrow. I did not. So to make the file that we're looking at right now, I did not require the kinematic fit to converge, but I did the other mass cuts. So
What is the kinematic fit doing?
I'll get to it in a few slides, but it's
But he said
show you how to turn it on. But we aren't doing it yet.
You had applied the kinematic fit, just not to this.
Sorry, the kinematic fit was used to make the data we're going to look at tomorrow, but not yet today. All right, it's done. Let's take a look. Maximize. All right, so now we have some new folders in here. So we histogram the particle ID. We'll get to that in a second. First, let's just look at the pi0. Yikes, that's a lot of background. So
He knows.
I warned you. All right, so yikes. So let's look back at the
There is a delay.
number of reconstructed objects. All right, I'll keep that in mind.
You You have to feign surprise a little better than that.
All right, so on the far right, we can see how many neutral showers there are. Typically in these events, there's 7 or 8 showers, and sometimes up to 25. So yes, when you make all combinations of those things, you'll have a lot of background.
It's already with the 100 MeV cut. This is already in.
I think so. Yes. Now this is Pythia data, so it's not just the omega events in this data sample. There's a bunch of different things, but also the clustering. There's some issues with the clustering. And keep in mind this is log scale. So if I go back and actually let's just pull up this one. So this is the 1D. So at the moment we've got a lot of neutrals to work with to match to just 1 pi 0. Okay. All right, so if that's what the pi 0 looks like, I bet you can imagine what the omega looks like. It's this one here. Yikes. Where's the omega? All right, don't worry. We'll have something at the end.
Again, premature yikes.
Okay, we'll have something at the end. And here's the missing mass squared. Okay, this needs a lot of work. All right, but don't worry. We'll do that. All right, so first of all, though, I need to talk about selecting the beam photons. So we have 60 to 80 in these data, 60 to 100 beam photons in each event, because we have a long readout window, and the beam is coming every 4 nanoseconds. So the way we do that is by looking at the RF time, or the signal from the accelerator. The accelerator is more or less telling us with a signal when the beam is arriving, which is every 4 nanoseconds. And we read it out in several of our detector systems, including the Cayenne and the TOF, and it has a very high. We read it at a very high resolution at 25 picoseconds, and it's even better than that because it's coming so often. We're going to read it out about 10 times per event, and it's average, so it's a very high resolution reference time that we have. So all of the timing from GlueX, all the detector systems are calibrated against this. So, there's our number of beam photons. All right, so what we can do is we can use this high resolution time as a reference for not just selecting the beam photon that matched our event, but also doing timing particle ID. All right, but first we have to make sure we pick the right one, because this is a signal that's arriving every 4 nanoseconds. We need to pick the one that corresponded to all the tracks that we're reconstructing in the event. So the way we do that is all the tracks vote.
One question: this background level then also emerges from mixing events, so to say. This is what you say, or?
Yes, certainly. Ideally, this is we're hoping this is a pi plus pi minus 2 photon proton event, but it could be other things entirely.
This is Monte Carlo.
This is Monte Carlo, but it's Pythia. So there's many different final states in this data.
We don't have out of time
There's no
events.
pilot.
Okay,
There's no hadronic pilot.
Right.
We have out of time beam photons.
Right.
Electromagnetic.
Electromagnetic pilot, but not hadronic.
Right. So there aren't any out of time events, so to speak.
Yeah, there shouldn't be, but we still don't know which is the right. Okay, in simulation we do. Experimental data, we don't know which is the right one. All right, so we can use this. So what happens is all the particles in the combination, all the pions and photons, you take the timing, from the time of flight detector and you project it back to the target and you see which of those 4 nanosecond bunches that it matches. And so, the proton votes on that one, and the pi plus votes on that one, and the pi minus votes on a different one. Well, hopefully that doesn't happen. But they vote, and hopefully you pick the right one as the start time, essentially what effectively is the start time for the event.
You end up with Donald Trump that way.
All right, so doing this selection, it happens automatically. Under the hood, you don't have to do anything. It's already done. So you can actually look at it. So comparing the RF time to that of the particles when they vote, you get a spectrum that looks like this. And it's cut off at plus or minus 2 nanoseconds because the signal is every 4 nanoseconds. So you can see that most of the time the particles are voting, you know, they're able to pick out something pretty well, although you have some grass on the sides. All right, so then if I look in this folder, when I'm building the combinations, what it's doing is it's taking the beam photons and it's comparing them to that RF time. So we generated all of these. Most of the time, the beam photons course, you know, comparing it to the RF time that we selected previously with the votes. So a lot of the time, you know, the photons are corresponding with the one we picked. And sometimes, you know, we have extra photons. We had 60 to 100 photons. And those are coming from different beam bunches. So you can see those different beam bunches here. One at 4 nanoseconds, one at 8 nanoseconds, etc. So basically, you just place a cut here to select the beam photon that you want, and so that you don't get any of these, the ones that are out of time with the tracks. Right? Does that make sense? So how many photons survived that cut? We started from 60 to 100, and surviving that cut, typically 1 or 2 or 3. All right, so we reduced the background quite a bit. That happened automatically. You didn't have to do anything. The only thing was placing the cut, which was coded automatically because it's standard. This right here, set max photon RF delta T. Whatever the beam bunch period is, we grab from the calibration database. It's 4. You know, you cut, you know, plus or minus 2. That's automatic. It's automatically done. All right, so we've selected the beam photon. Sometimes we still have, you know, more than one, but at least we've narrowed it down. So now let's do particle identification. All right, so the first thing we're going to look at is dEdx, you know, energy loss in the drift chambers in order to do proton-kaon separation. So I'll show you this plot. It was made by this action, dehistogram action PID, which we ran with. So we'll be able to take a look at it. But it's going to look at the plot looks like this. And so what we want to do is place a cut to separate the protons and the pions. So the idea here is that the red curve is designed to cut away everything beneath it. Cut away all of the pi pluses, or cut away some of the pi pluses while keeping all of the protons. And the magenta curve is designed to select pions, to cut everything above it, cut all the protons while keeping all the pions. So, you know, this is the kind of cut we want to do. So in order to make a custom cut, you know, there isn't something that just pre-coded in the analysis library for this. This is something that I made using this Perl script, which generated some template code to use, and then Justin tweaked the cut to match the Monte Carlo. But we want to use it, so that exists on the disk somewhere else, and we're just going to copy it in. So this is the one thing I didn't want to do from scratch. So it's in here, in our reference plugin. All right. So I'm just going to copy the files. Okay. All right, so then now we want to place that cut. So go back to our reaction. Include the header file. All right, so we're going to include another action here for cutting particle ID. So it's going to look something like this. So just add another action, but it's called this instead. All right, let's look at the header file. See what it's supposed to be. All right, we want max rejection to be false. So just do false. Then I could give it a unique name, but I don't need to. So, all right, that's it. That chunk of code was made by the Perl script, and then we modified it, and it's got the cuts in here. So you can look at it and see what it does, but I'm not going to spend time on it. So here what's going to happen is you histogram the particle ID. All particle combinations will then place the DEDX cut. And then all particle combinations that survive that cut will then histogram the mass. So these things act sequentially. So you can place cuts, and you won't consider those anymore.
That means if you would put the cut on the DADX before the histogram action, then you would in the histogram only see the cutted rest of the series.
So in fact, sure. Why don't I do this? I'm going to just histogram the particle ID twice, and then post DEDX cut. All right, it's that easy. So we can see what it looks like before and after. All right, so let's see if this compiles. Oh, right. Oh, this is the wrong name. It's decustom action. Sorry about that. Right, decustom action. All right. Try again. Yeah, the header file and the name of the class. That was for the DEDX cut. All right, so now let's run again. So now we're histogramming the particle ID information before and after. So we should be able to see that DEDX cut before and after the fact, and hopefully it worked. All right, while that is going.
Like a cooking show.
Well,
Always
the
wanted
butter,
it to really
well,
be
the
cooked,
butter
right?
is.
Well, that's in the oven.
Well, I'm
All right.
lazy.
So let me say, be careful a bit, because we're doing this with Monte Carlo, but the resolution in Monte Carlo is different than the resolution in the experiment. So if you're going to do a cut with some functional form like this, you better be careful the resolutions match between them, or else you'll cut a different amount in Monte Carlo in data. So in this case, it's safer to do a confidence level cut, which takes into effect the resolutions, but we don't quite have the uncertainties ready for that yet. All right, so this is almost done. I just did the first 10,000 events. All right, so let's blow this up. So particle ID, do color. So these are the candidates for the proton, what we think the proton could be. All right, this is CDC, DEDX. So this is what it looks like before the cut. And then after the cut, it looks like, oh good, ions disappeared. So before, after. Success.
Yeah, you seemed actually surprised.
But you could tell he was.
When you're doing it live, you don't want to take it for granted, right? All right, so now there's other things too.
What rabbit in my hat?
So let's look at the timing. Let's look at the timing and the time of flight for, say, the pi pluses. So this is beta versus p for all of the pi plus candidates hitting the time of flight. So you can see the strong pion band, but you can also see some proton background. So we can cut that out, and the way we're going to do it is we're going to look at delta t. So we assume it is a pi plus. We propagate the time from the time of flight back to near the target. We compare that to the RF times. That's the highest resolution time we have. And you can see the pi pluses have this narrow band 0, and then the protons are this background up here. So we can place a cut on this. And then same for, so for example, we could also look at protons hitting the barrel calorimeter. And let's look at beta versus P there. We don't have enough statistics, but you can see the proton band and some pion band stuff up here. And I should point out that this is old simulated data before some improvements. This was several months ago. So the resolution's a little better than this. The clustering's a little better than what we're showing now. But we can place cuts in the timing in the barrel calorimeter as well. All right. So compare to the RF timing cut. So let's just go ahead and do that. Wait, here we go. All right, so I'm just going to keep this as simple as possible. What we're going to do, so we have some example code that's been commented out. Let's do PID delta T cut. So false, we're going to use measured data. So the default was plus or minus 1 nanosecond. Let's change that to 2. And then, so for right now, this is written such that, we do a cut on all proton candidates hitting the time of flight, plus or minus 2. So you could tweak it however you want. What we're going to do is a special case. Unknown means every particle. And cis null means every detector system. So just every particle, every detector system, plus or minus 2. Going to let it go.
Plus or minus 2 from?
On that delta T. So for example,
minus R, right?
the pi plus time of flight, this plot, delta T between, you take time and the time of flight, project it back to the center compared to the RF.
But always assuming the pion with every.
Well, in this case, so when we're looking at.
Okay. So depending on what assignment
Right.
is given now, does it meet expectations when it hits the time of flight?
Exactly. So for the pi plus here, we want to cut everything that doesn't look like a pi plus, basically. So delta.
What is the unit of the plus minus 2 cut?
Nanoseconds.
Simply
In general, the units of default are nanoseconds, centimeters, GeV.
because when you say for either system you're applying this flat cut, so to say,
Right.
probably the best cut would depend on the resolution of the system.
Yeah. There's absolutely some caveats. I don't want to go into details, but our cuts, the resolution changes with momentum, not just detector. It's better to do a momentum-dependent cut. Also, resolution might not match between Monte Carlo and experiment, so it's even better just to do a confidence level cut, which we could do, but the uncertainties aren't quite ready for the experimental data. So we're just going to do something simple for now, and you can do more complicated things on your own. Okay. So now let's go again. Quit. We've added some particle ID cuts. So let's compile. And let's run 10,000 events. Now we'll look at the mass histograms to see if they look any better. Hopefully they do. All right, so next up will be kinematic fitting. I guess I can start talking about that while this is running. So the idea with the kinematic fit is we want to fit the data, and we want to know are the events in the file the reaction that I want to look at. So does the data match this channel? So the idea is you constrain the data to match your reaction, and there's several different types of constraints you could do. You can require energy momentum to be conserved, which is good for cutting out events with extra tracks. You can require the mass of the gamma matches the mass of the pi 0, and you can require that all of these can come from the same vertex. So the idea with what the fit does is the fit adjusts the track measurements and shower measurements in order to satisfy these constraints. So you get some adjustment of the parameters, some delta x. And the idea is you want to minimize the chi-square of the fit by minimizing how much the measurements you had for the tracks had to change in order to match your constraints. In other words, if you had a whole bunch of extra particles you'd have to adjust the momentum of your tracks by a lot in order to conserve momentum. That gives you a huge delta x relative to the uncertainty, and that'll give you a high chi-squared on the fit. So to select your events, you could just cut on the confidence level of the fit. And you can apply all these constraints simultaneously. Okay, so but before we do that, this is finished, so let's just look at the results here. So now, let's blow this up. All right, so what we did was we cut on the particle ID here, and then we histogrammed the masses here. So we histogram the mass of the pi 0 now. Okay, that looks a lot better. Before we could barely see it. Now it stands out, but there's still a lot of background. Missing mass squared. All right, we have a cleaner peak than it was before. And the omega, oof. All right, don't worry, we'll get there. Oof. All right, kinematic fitting will come in and save the day. So when you do the kinematic fit, don't just assume it worked. Make sure you check the fit results to see if they're okay. So the poles of the kinematic fit, in other words, what this delta x was relative to the uncertainty for each parameter, should be a mean of about 0 and have a Gaussian width of about 1, plus some background tails on the side. And the confidence level should be flat for your signal and have a spike at 0 for the background. And there's documentation on how it works there. So, okay, let's do the kinematic fit. Let's close root. Okay, let's go back to the code. Let's do the kinematic fit. Here. There we go. Bam, that's it. All right, we're doing the kinematic fit now. So what this does is there's several different kinematic fit types you can do. This is going to constrain the forward momentum and the vertex fit. Everything comes to a common vertex. And this shows you the different options up here. Now, the mass of the pi 0 is automatically constrained unless you were to set that flag to false. But we want to constrain the pi 0 mass, so let's keep it on. All right, so now what we want to do is we want to histogram what it looks like. So let's just uncomment that line. Kinematic fit results. And here I'm going to require that the kinematic fit converges. So I'm going to cut on the figure of merit or the confidence level of the kinematic fit at 0. So as long as it has a number, meaning it converged, we'll take a look at it, see what it looks like. And this 5 is just a cut on looking at the poles. It's not. Don't worry about it.
What does it give you if it doesn't converge? Negative or something? Or
I think it's not a number. I can't remember.
So the photon momentum direction, what do you use for origins?
Okay. So it depends what kind of fit you're doing. If you're just doing...
What we're using before the fit?
Before the fit, okay. So the photon's just some shower in the calorimeter, and you need a starting point, a vertex somewhere in the target to get the momentum. So by default, what it does is it looks at all the tracks in the event, and it fits them to a common vertex, and it uses that point to define the momentum for that shower. Now, if we were doing a P4 fit, that you would use that momentum. But since we're doing a P4 and vertex fit, instead what it does is it's going to treat the shower as if it was just a point in space with some energy. And after each iteration, as we change the vertex position, recompute the momentum and continue with the fit.
So that pre-kinematic fit
Yeah.
is what?
The D-vertex factory. I'm not going to go into it.
Okay.
It just happens automatically. Don't worry about it. The idea here is I'm just interacting with the interface, and everything's happening underneath, and it does it for you, and you don't have to worry about it, right?
you look at the results and then you look at the results and then you worry.
Yeah. That's a long way of saying shut up, Mark.
He's polite.
All right, so we want to look at the masses again after the kinematic fit. So I just took this code and copy-pasted it. Okay, let's keep same. Okay, let's.
Oh, the screen just changed for some reason.
Crashed.
In comparison to the TV.
Uh-oh. Firefox closed. Well, I'm still sharing on Blue Jeans. Just people. I don't know. Can you read it up here?
Well, let's see what happens.
All right, I'm going to keep going while Mark's trying to get it back. Basically, I'm just taking the histogram code, copy pasting, then I'm going to histogram it after the fact, and I'm going to change the names of the string to make sure it's in a unique folder. And then with the omega here, so with the omega, I'm going to histogram it twice, once with the false and once with the true. So the idea here is that the false was using the measured 4 vectors, and the true is with the kinematic fit 4 vectors. The omega mass itself is not constrained in the kinematic fit because it has a non-zero width. So, but what we get should be narrower than it was before.
Due to the vertex and P4 constraint, so to say.
Right. So it doesn't matter. Save. Is there anything else?
Probably losing your audio recording now, right?
Sure, is that still connected?
Yeah.
So you're sharing your desktop?
Yes. Those of you who are remote, can you hear me?
Yes.
Yes.
All right, we're good. All right. Okay, so let's compile and run. All right, so when does the kinematic fit actually happen? It doesn't happen until you need it. So, in other words, we did all of these things that didn't require kinematic fit results until this step, this kin fit results. So, all of those cuts happened, on particle ID, etc. They happened before the kinematic fit, so you aren't going to kinematic fit any combinations that failed there. You're just going to kinematic fit things that made it up to the first time you needed the results.
You just clicks on the workshop and go and launch it. I was saying click the workshop and go launch Blue Jeans.
Go ahead.
From the previous screen. I don't know where it was.
Firefox crashed. You need to bring it up again.
Yeah, he's got it up.
So where were you? Just gonna go to the workshop and go to Blue Jeans, right?
Yeah, go back. It was open a new tab. The thing was there.
Where?
Just open a new tab. All right. Thank you. You got it. All right, we're back just in time. Kinematic fit finished. Let's look at what happened. Yes. I have to click record here. All right, so this is after the kinematic fit, the mass of the pi 0, where I've put a cut at a confidence level of 0. So in other words, every combination that fit didn't converge is not there anymore. So this is what it was before, and this is what it is after. So in other words, just requiring that kinematic fit to converge, cleans up the pi 0, a fair amount.
This is now without a pi 0 mass constraint, right?
The pi 0 mass constraint is on. So I'm just, if I were to look at the kinematic fit for vectors, it would be a spike right at the mass.
Right.
So this is showing that we're still selecting background even with that constraint. But I have I could put a cut in the confidence level that's greater than 0. I just haven't done it yet.
So it's like this is the raw pi zero mass after the fit converged.
Yes.
This is somehow this is already the fitted with the pi zero mass constraint.
Yes.
You say
Yes. So this distribution is biased, absolutely. But it just show that there's still some background, just requiring the fit to converge. But at least it's less so. But let's look at the confidence level from the fit. All right, let's go log y. So we see this giant spike at 0. Change the binning. All right. So hey. All right. So the full, if you're in SimRecon, it's in the libraries analysis, and there's a whole bunch of different kinds of things there. Show you what's pre-coded, or you can make your own. But the idea is you add them here in sequence, and they'll be executed in order. They just have a common base class, but the inherited class can have whatever name you want. All right, so this is done. Let's look at the results. Let's hope that the omega looks good. All right, let's just skip to the end. The omega maximized, measured. This is the measured for momentum. What the omega looks like, the measured for momentum. This is what it looks like with the kinematic fit. So there's no constraint on the kinematic fit on the omega mass, so this is unbiased. So this is a small sample of data. There's about 3 times that on the
Sorry, what was the last bit you did? I was trying to.
So, right, for those of you watching.
Confidence level.
For those of you watching the recording, which has just started again, I put a confidence level cut at 0 just to force it to converge, and then I did one again at plus or minus 5 sigma. So I could have cut it higher at 1%, 5%, but there's no point. We already have a pretty clean omega. You can already see that pi 0 is pretty much, the cut's only selecting events near the pi 0 mass is what this shows you. There's not much background left. You could keep cutting tighter, but there's no point. So that's what that shows you. All right, and then here at the end, this was automatically there at the bottom. This particle combo kinematics. In other words, the kinematics of all the particles in the combo. So, we can look at the pi plus and the omega, t versus theta. This is where it is. It looks prettier if you have more events, of course, but handy information is already histogrammed for you. Right, here's the vertex Z. The target was 50 to 80. Okay. So another thing we could ask is, so we had all those combos. How did they do with all of our cuts? So what we're histogramming here is, make this further out, the number of particle combinations that survived each of our actions. So first, requiring that there's just at least the minimum number of traction showers, you had 60,000 combinations in total for all these events. But you start placing cuts, the DDX cut, just right off the bat, really cut it down. And then cutting on the particle ID timing, really cut it down even further. Kinematic fit confidence level, even further. And then, requiring it to converge first, and then at plus or minus 5 sigma. And this shows you all the actions that were called. So it's just the number of combos that survived, number of events that survived. Here's number of combos that survived in 2D, where the y-axis is log scale. So you can see, by the time you get to the end here, most of the time you only have one particle combination in these events. So even though we had sometimes 1,000 to start with, just putting all these cuts just naturally pared it down. So the idea is, by default, there's hardly anything happening, just those pre-select cuts on the tracks and showers, but it's easy to apply cuts to do particle ID, etc., to help clean it up. All right, now we could keep doing stuff in Jana, but it's faster to do things in root. So how do we get our results into root? So, well, we need to do a couple things. I guess first of all, I should go to my slides. Where are my slides? Here are the slides. All right. So in order to save to root, what we need to do is we need to enable it in the D reaction, enable the fact that we want to save it to root, and uncomment some code in the processor again. So this is D reaction. Oh, look, there's this thing, enable T-tree output, uncomment it, okay. Now I need to, so it's telling it, go ahead and turn it on and just save it in that file. But then in the processor, again, this is what Jana actually is running. I need to go to the top here, B run. This section of code is run every time a new run is started. So as long as, so the first time this happened is what it does is it gets the event writer root from Jana, and it creates the data trees. If you're running over two different runs for some reason, it won't create it the second time. So it'll create the trees, and then we need to tell Jana to write. So that'll do it. That'll fill the trees. In fact, we can get rid of this code entirely now. So in the D reaction.
How do we specify the reaction?
What do you mean? You could have any number of reactions.
This is all existing reactions. Go ahead and put it in the root tree.
Almost. It will. So this will create it for all reactions, any of them that have the enable flag set to true. And this will fill all of the ones labeled session 2, which was what I created the name of.
That's the reaction.
Yeah, technically it's the factory tag, but whatever, as long as
you're consistent.
Yeah. So Jana is on demand. So this is the only thing that's actually executed. This D reaction, we were telling it what to do, but the thing that actually does it was the processor. So the processor, every event calls this function, and the only thing in here that's uncommented is this. We tell it to fill the data trees. So what does it do? The event writer says, okay, in order to fill the data trees, I need the results of the analysis. The analysis says, okay, well, to get the results of that, I need to actually do the analysis. To do that, I need to make the particle combinations, and then I need to apply the cuts. It all happens under the hood automatically, and that's all you need to do.
So this is the only thing we put into the event processor so far?
Yes, that's it.
Okay.
So let's rebuild. And so what's going to save to the tree all the combinations that survived all of those cuts. And then you can do more things in root later, like we'll do tomorrow.
So we were getting all those histograms from the histogram monitor histogram plugin.
So when you were getting the analysis results, when it gets the analysis results, it goes through and does all of those analysis actions. So here in the reaction factory, we specified all of these actions. So to get the results, it just goes through in sequence and executes these.
But where did we ask for results? I remember you putting that in there.
So it was in the processor event function.
It was, okay.
It was.
You just took it out.
I just took it out because it's automatically going to happen inside of here.
It happened just if you asked for the tree.
Yep.
Okay. I didn't see you take it out.
Right, because there's some delay.
This applies to the data and the Monte Carlo.
This stuff will work for either.
And in the Monte Carlo case, you keep the generated accepted Monte Carlo stages.
We will do some of that tomorrow. the generated, we don't even have to pass through the event selection, right? So we're just going to keep that straight for the for the amp tools at the end, I think. Right, Mike?
You keep it.
Yeah. So I mean, we could pass it through here if we wanted. Yeah, this is also in the root tree. It will have the thrown tracks in there because it will recognize this is a Monte Carlo thing. But we'll take a look at it tomorrow. Yes.
At the beginning, you showed all the different combinations you had in one event, and then after the analysis, there were a couple of events that were still two combinations.
Yes.
So you filled the tree twice.
I filled it. So the tree will have each event will be one entry in the tree, and there will be information in that event for both combinations, or all three, or all four, or all 5,000, or whatever's left. It'll be there for all of them. All right. So now, if we look, we have a root file, tree session 2. That's what we called it, and we can look at that tomorrow. All right. So in summary, it's pretty easy to get started, get into root. Notice how I didn't do anything with tracks or for vectors. You can certainly do things. You can make custom actions and do custom things. It's faster to do them in root. So we're just going to get through to root, and we'll do some more stuff there. So, but there's a lot of common things that people can want to do. Histogram, particle ID. Instead of writing all that code yourself, just uncomment that line, and it does it for you. So to remind you, the final analysis that we did for the workshop, we didn't have hardly any cuts in JANA. We just had those initial skim cuts, wide around the pi 0, wide around the omega, wide around the missing mass, and we require the kinematic fit to converge. That was it, to get to root for tomorrow, because we want to show you how you can look at particle ID in root. So see tomorrow's talk for further analysis. And so time is up. There are some exercises. You can look at it in the README. It looks like a lot of work, but guess what? You just need to ask them analysis actions, and it'll do everything for you. All right. Any questions? No?
Yeah, one question concerning fitting is, is there a possibility to handle displaced vertices, K-short stuff? Probably there is.
Yes. So, right, the kinematic fitter will do multiple detached vertices. So even if you have like a cascade, it'll do all 3 vertices, and it will use decaying particles themselves to help constrain the vertex.
See, so automatically it knows that if it's a long-living particle, it takes that into account. Great.
You can set up the kinematic fit manually if you want. There's instructions on how to do that, but you can also just do it automatically.
Where's this README file? In which directory?
It should be on your virtual machine here.
Is that on the workshop?
It's not there.
Dollar workshop.
I thought that pointed at the same spot.
So you guys don't have to do it now or anything. I'll hang around for a bit in case you want to take a look at it or if you have more questions. But that's all I have. Any further questions?
Thank you very much. Very good. That's awesome. Very good.
Yep.
Thank you. I think we can just. So, what's the safest way to stop the virtual machine without?
So if you want to turn off the virtual machine, just act like it's a computer. So up here at the top left.
You just close the window and save machine.
Oh, it's got a power thing.
Yeah.
Yeah, but you could also power off, hit the power button here.
That was up in that little where it's like a bird or something.
Try to close the window, you can save machine states and get you right back to the system.
So also there's 35,000 events of Pythia data on the virtual machine. There's much more on tape. You can set it up to look at whatever channel you want, play around with it. But It was in the slides near the beginning.
The accepted way to work the results. You give them most
Yeah, it's on the post the slides here. They have the whole. We'll talk about accessing the data on the
You're talking about like an asymmetric PDF?
Okay, you're sharing the desktop.
Well, yeah.
I'm not sure. Okay, so the desktop is fine. I'm going to stop the recording.
Okay.
I'm going to log in as moderator here. And that'll keep the meeting going. And then log off as moderator. Someone must be logged in as moderator. Did the meeting ever stop? No, it never did. It did stop. Oh, it did stop.
I think it must have been that computer when it went down.
Right. So,
But it will have to remain that computer, though.
right now, so there's a moderator in the meeting that's keeping it going. Right now, that's my laptop. Okay. So I'm going to make this a moderator, then I can log off the laptop.
So we should link the location of these recordings to GlueX. Of course. That's what we're going to do.
Please do it.
Okay. That's I just wanted to.
Yeah, I'll figure it out.
Okay. All right, I can do this. I'm just gonna ask Mark what it is.
When should we expect the recording to be uploaded?
I don't know. We gotta figure out how to do it.
Oh, okay.
I mean, it's already on the web. It's a question of downloading it from BlueJeans and re-uploading it somewhere.
Or he has to post them.
Okay.
Well, I guess we can send out an email if you want.
Or just putting the link on the website. Oh, well, an email, yeah, will let us know that it's
on the BlueJeans site.
That would be great, yeah.
Okay. We're doing everything with a Curtis meeting.
Yeah, gotcha.
We should have done this as a Paul meeting.
Yeah, so Paul, Curtis needs to download these files and put them on the queue and tell us.
Yep.
Okay.
Okay. One thing.
So then.
That's right.
Yeah,
one thing that he can do immediately without downloading it is he can go into the recordings tab or recordings page at BlueJeans and mark it as recordings.
You said that. Well, maybe you should finish what you
So
I have to create my own meeting page, or I have to log in as Curtis.
Right. So then I think you have to.
If you had a Chi-square surface, you could just
yeah, one thing that I thought about mentioning is that when you're running Gen, all this stuff automatically works as long as you're connected to the internet, right? If you're not connected to the internet and you don't have magnetic.
Oh, that's why we downloaded it ahead of time.
Yeah, I know, but I mean, it's at some point you may need to remind people. Like,
As far as I'm concerned, there's a million things I need to remind people of, and there was only an hour's worth of time.
Oh yeah, that's why. I mean, I was going to bring it up and then like
30% of that.
Huh?
Turned out pretty well.
You're still good.
Yes.
Oh, right.
Yeah, it's still fresh.
Okay, I think that.
You can just go ahead and end the meeting.
Now the. Well, the other question that comes up sometimes is that whatever that variable that you're measuring has some physical range. The question is, do you integrate it in the physical range? Or how much you
We'll be facing that problem as well.
Yeah.
So, for example,
often like you're measuring the square of a number. When you do your toy Monte Carlo, there's some
Will that video be up tonight?
Probably not. Unfortunately, what happened was because we were using Curtis's account, he has to be the one to do it.
Okay.
Tomorrow, we'll make sure I do it. But it'll be up eventually.
Or do you
So how do we
integrate
integrate
the
this?
region, take 67%?
Is it still recorded?
Yeah, I'm trying to end it now.
That would be
My Firefox hung.
Everybody's Firefox.
Okay, so what he can do is he can mark it as shareable and send us a link. Okay, as a start, and he can also say that other people can download it. You know.
Yeah.
Perfect.
Okay, but to get to the recording, you have to log in with your JLab account at the Blue Jeans site. You know.
Well, okay, people have JLab accounts, so that works.
I need to send an email, and then I will answer whatever you.
Okay.
And often what you measure is not the read itself, but the thing about it is what you measure and what you measure could have functionality such that the number that you extract is.
So this is like we have basically we have rather large and size.
In that case, your extracted values of the individual components.
Yes, so the arrays are arbitrary.
One fluctuates up, the other does fluctuate down. So has the fluctuations that you measure in the experiment.
Right. Have you ever seen that interview with Richard Feynman where the interviewer asked him how magnets work? He essentially refuses to answer because he can't explain it in a way that the guys can understand. So he spends a lot of time explaining to him why he's not going to explain how magnets work.
Nice work.